finish up section 8.3 today. So this will finish up chapter 8 for us. Yep. So the tentative plan would be to do the chapter 8 test on Thursday still. We'll see when we get done here. All right. So just as a reminder, some of our basic probability properties. So probability is always a number between 0 and 1. The probability of all events in your sample space has to equal 1. If your outcomes are equally likely, we can calculate a probability by just looking at the number of outcomes in an event divided by the total number of outcomes. And then the complement rule, if I'm looking for P not, the probability of not A, we can do that as 1 minus the probability of A. So one of the things we'll be interested in when calculating probabilities, and often in the real world, is calculating expected value. So to calculate an expected value, you want to talk about it's going to be the probability of success times the total number of trials. When we do the expected counts, that's essentially what's happening, right? If you think about the probability of success, that's basically the row total times column total. And then if we divide each of those by the overall total, that's the probability of each one of those happening. So if you flipped a coin 100 times, you'd expect 50 tails, right? 1/2 times 100. How many tails would we expect if we flipped it 25 times? 1/2 times 25, 12.5. Expected values don't have to make real world sense. That is totally fine that you got a decimal value for an expected value. Everybody's cool? Okay. Again, talking about mutually exclusive events, because these come up a lot here in this next section. So we say that events that are mutually exclusive have no outcomes in common. Basically, the intersection of those two sets is empty. So the probability that the two events can occur together is 0. So like if we ask the probability of selecting an individual from this room that is female and over 40 years old, the probability is 0 because those are mutually exclusive events, right? There's no person in the room that's both female and over 40 years old. Everybody's cool? Okay. So if we have mutually exclusive events, we can calculate the probability of a union just by calculating the probability of the first event and adding it to the probability of the second event. Only if the events are mutually exclusive. So this formula only works when events are mutually exclusive. So an example here, so say we have this two-way table and we're choosing a student at random. Find the probability that a student has pierced ears. What would the probability for that be? 103 out of 178. So we have a total of 103 students with pierced ears, 178 total students. How about male and pierced ears? What would that probability be? 19 out of 178. Very good. Are these mutually exclusive events? No, right? Because there are 19 people that have both attributes. Everybody's cool? Okay. Male or pierced ears. So you'd want to count 84, 19, and 71. right? Those will include all the males and all the people with pierced ears are those three. What you want to be careful about is you don't count 103 and then 90. Right away, if you did that, you should notice something's wrong. How would you know something's wrong if you counted 103 plus 90? It's bigger than 178, right? Automatically, you know something is up. That seems fishy. Or you could have done it as 1 minus the probability of not male and not pierced ears. So you could do 178 minus 4 over 178. Everybody's cool? Okay. So if we take this two-way table and we convert it into a Venn diagram, again, we've been doing this for a couple of lessons now, going back and forth between two-way tables and Venn diagrams. So you get something like this. So you have the two overlapping circles. You start with the intersection first, that's the 19, and then you fill accordingly. So from a vocab standpoint, if I'm looking for A intersect B, that's the 19. If I'm looking for A intersect not B, that's the 71. If I'm looking for not A intersect B, that's the 84. And not A intersect not B, that's the 4. Everybody's cool? Again, we did very much the same kind of thing on the quizzes, right? We've been doing it for a couple of days. Yeah. I have them done. I can give them to you at the end of the hour, certainly. We can use the addition rule for mutually exclusive events, or cannot use, right? So what do we do if we have overlapping events that are not mutually exclusive? Well, we can count everything in A, and then we can count everything in B. But if you notice that what we've done is we've counted that intersection twice. When we counted everything in A, we counted the intersection. When we counted everything in B, we counted the intersection. So we double counted that region. So we'll just subtract it off once. So this is our general formula for calculating the probability of a union, whether the events are mutually exclusive or not. So far, so good? So again, two different formulas, right? This formula still works even if the events are mutually exclusive because the intersection has probability 0, so it just turns back into this formula up here. I always just think about this one and then put a 0 in if it's empty. The next thing we want to do is talk about conditional probability. So let's start with the idea that events are independent. That means the previous outcome has no effect on the next outcome. So example, if you're flipping a coin, those are independent events because the previous coin flip has no effect on the next coin flip. Or if you are, playing roulette, where the ball landed on the previous spin isn't going to affect the next spin. But if you're drawing cards out of a deck, what happened on that first card that you pulled out will affect the probability of the next card because you've removed a card from the deck, right? So those are not, that would be an example of something that's not independent. It's conditional, unless you pull the card out, you look at it, and you put it back. Now it's independent again. Is everybody okay with that idea? So if I want to calculate the probability of an intersection, if the events are independent, just going to be the probability of the first event times the probability of the second event. So if I wanted to find the probability of flipping a coin and getting heads 2 consecutive times, well, the probability of getting heads the first time is 0.5. The probability of getting heads the second time is 0.5. So the probability of getting heads 2 times in a row would be 0.5 times 0.5 or 0.25. Is everybody okay with that idea? So again, if it's an and, you're multiplying the probabilities together. If it's an or, you're adding the probabilities together. Everybody's okay with this? Okay. And again, intersection means and. So oftentimes the key word to deciding whether a situation is independent or dependent is whether there's replacement going on. So whether you're drawing like names out of a hat or drawing cards out of a deck or like picking clothes out of a closet, if you're replacing the clothes or the names or the cards after you've drawn one, if you put it back afterwards, you still have independence. If you're not, like once you've pulled a name from the hat, you're going to leave it out and then pull the next name, there you've created dependent events. So this term of replacement is often our indicator for independent event versus without replacement is our means dependent event. Everybody's cool with that idea? We've kind of hit on this a couple of times. So again, if you have 5 green gummy bears, 4 red gummy bears, and you pick one green gummy bear, the probability that the second gummy bear will be green. Well, if you're dealing without replacement, how many green gummy bears are left? There'd be 4 now. And there's 8 total gummy bears left then. So the probability of getting a second green one would be 4 out of 8. Everybody's okay with that? If we are replacing it, well, then there's still 5 green gummy bears left and 9 total gummy bears. So the probability with replacement would be 5 out of 9. Does everybody feel good on this? Pretty straightforward, right? So common misconception that mutually exclusive and independent don't necessarily have anything to do with each other. So for instance, if I flip a coin twice, that's mutually exclusive and independent, right? Because the events are heads or tails. Can't get both heads and tails on a coin flip. Mutually exclusive. Independent because one coin flip doesn't have any effect on the next coin flip. That's independent. In a deck of cards, you pick 2 cards and examine their suits. For example, getting diamonds and spades can't happen at the same time. Those are independent. Mutually exclusive. But because I've drawn a card out, that when I pull the second card out, that has changed removing the first card has changed the probability of whatever can happen in the second card. That would make those a dependent event, right? Because the first draw was out of 52, the second draw is out of 51. But if I, instead of drawing 2 cards and then looking at them, if I draw 1 card, look at it, put it back, draw a second card, look at it, now that's, again, still mutually exclusive if we're talking about 2 suits. But because I've replaced it, the first card before drawing the second card, it is now independent. Everybody's okay?
The first card is independent because...
So when we talk about independent, we're always talking about comparing 2 events, right? Does one event affect the next event? So drawing a card, looking at it, putting it back, doesn't affect the probability of drawing a second card because your second card is still being drawn out of 52. If I take the card, look at it, and set it down, draw a second card, the probability of drawing that second card is changed because it's now being drawn out of 51 instead of 52.
And it's independent if it stays the same.
Yes.
the probability.
Yes.
Okay.
Yes. All right. So this is a situation where we're looking at blood types in different countries. So these are just the blood types of randomly chosen people from these 3 different countries. And we're asked, what is the probability of blood type AB in the US? Well, what should the probabilities add to in the US? Should add to 1, right? So if I just take 1 minus 0.43 minus 0.41 minus 0.12, 0.04 should be my probability for AB. Likewise, same thing for Russia. So I'd have 1 minus 0.39 minus 0.34 minus 0.09. And that one is 0.18. Too much arithmetic for me to do at 8 o'clock in the morning. Everybody's cool? Okay. Dirk lives in the US and has type B blood. Type B can only receive from types O and B. What is the probability that a randomly chosen citizen can donate blood to Dirk? So you're asking to find the probability that the donor is O or B. If it's an or, we need to consider whether the events are mutually exclusive or not. Are blood types mutually exclusive? Yes, you can't be 2 different blood types at the same time. So all we need to do is add up the probability of O plus the probability of B. So 55%.
They weren't mutually exclusive.
Then you'd have to subtract the probability that you could be both, right? So I wrote it in, but you can't have 2 blood types that are this, person with 2 different blood types. Does that feel okay? Okay. Everybody happy so far? So again, the key to figuring this out was noticing that this was an or probability. So the mutually exclusivity was the piece that I cared about. Oops. What is the probability of randomly choosing a person with blood type O from the US and a person from China with the blood type O? So here we're looking for probability of O in the US and then O in China. So this is an intersection, right? So that is the case where we care about independence. Are blood types between countries independent? Is the person's blood type in the US going to affect the person's blood type in China? No, that seems completely implausible that that would be the case. So these are independent events. So the probability of O in the US and then the probability of O in China is just going to be the probability of O in the US times the probability of O in China. So 0.43 times 0.36 or 0.1548. Everybody's okay with this idea? This is why when you go on the gambling website or app and you try to do a parlay, the payout is so much better because the events in your parlay should be independent. So the odds are multiplicative, so you get much better return. but they're less likely to happen. Luke is getting his phone out right now. He's going to place a parlay, it looked like. It's like, oh, I get it now. All right. D says, what is the probability of choosing 3 people, 1 from the US, 1 from China, and 1 from Russia, and they all have type O blood? Yeah. So this is just 3 independent events. So it's just going to be probability of O in the US times the probability of O in China times the probability of O in Russia, or just over 6%. The takeaway here from this example is it doesn't matter how many things you are anding together. You know, probability of O in US and probability of O in Russia, or and O in Russia and O in China. It doesn't matter how many of those things you and together. Just as long as they're independent, you just boom, 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 multiply it out. Everybody's cool? Okay. What is the probability of randomly choosing 3 people, 1 from each country, all with the same blood type? So this would be both an and an or question, right? So you could have O in US and O in Russia and O in China, or A in Russia, A in the US, A in China, or B in the US, B in China, B in Russia, or A, B in the US, A, B in China, and A, B in Russia. Everybody kind of see how it's both an and an or statement? So, because it's or, and these are independent events, I know I can break them up with a sum. But each one of these events that we've broken up as a sum in our sum are independent events. So we calculate them the same way we did before. Everybody feel okay on what we did there? The trickiest thing is being able to read the question and be able to write it as like sets so that you can apply our formulas, right? It's going to be the most difficult part for us. If we get through this, translating it from the story into like P of whatever and whatever and whatever, we should be good, right? Another example, it says it is estimated 17% of all computers bought from one manufacturer require one repair job during the first month, that 7% will need repairs twice in the first month, and 4% will require 3 or more repairs in the first month. What is the probability that a computer will need no repairs? Well, let's start by like like defining some symbols so we can do this, write a probability statement that we can use our formulas on, right? So we'll say event A is 1 repair, event B is 2 repairs, and event C is 3 or more repairs. Everybody's okay there? Okay. And we have their probabilities. So I've recorded that up here. So if I have no repairs, that is mutually exclusive to the other events because I can't have 1 repair and 0 repairs, right? That doesn't make any sense. So no repairs plus the probability of A plus the probability of B plus the probability of C better give me 1, right? Because it's a probability space. Those are the 4 possible outcomes because it's 3 or more, right? So if I just rearrange this, if I subtract P of A, P of B, and P of C from both sides, I can do 1 minus or 0.72 or 72%. Everybody's okay? What is the probability that a computer will need more than one repair? So that would be 2 or 3 repairs, right? So it would be the probability of B or C. Oh, no more than 1 repair. Excuse me. I missed the no. Yeah. So it's going to be less than or equal to 1. So the probability of no repairs plus the probability of 1 repair. Yeah. Excuse me. Ooh, reading comprehension, guys. Those little words make a big difference, huh? What's the probability the computer will need some repair? What the heck do we mean by some repair? 1, 2, or 3, right? Very good. So just add them up. 0.28. So far, so good. It's feeling easier as we're getting more example. Or you could have done 1 minus our answer from no repairs. Could have done it that way as well. Does it make a difference which way you do it? Not a bit. Okay. If I bought 2 computers, what is the probability that neither will require repair? Not quite. This is going to be the probability of some repair and the probability of some repair. Right? It's an and statement because you have 2 computers. Everybody's okay with that?
Yeah. Some repair.
Well, it's because it's an and, it's times. Now the question is, are these independent? Is having to repair 1 computer going to affect having to repair the second computer?
No.
Not at all. They are independent. So we can just say the probability the first does not need repair and the second does not need repair. So that's one of those. So 0.72 times 0.72. Everybody's okay? So far? Yeah? Okay. Probability that both will require repair. Same idea, right? Probability some repair and some repair. Yep, or I did 1 minus times 1 minus, but yeah, you get the same result either way. So just under 8%.
Wait, how do you know you the calculator?
You could have done 0.28 there also.
What was 0.28?
Does the probability that of some repair? So if you went back a bunch of questions, that was one of the things that we answered. There it was. Need some repair. So that was a previous answer. Is that cool?
Yeah.
Okay. All right. So what happens if you don't have independence? What if the events are dependent? Well, what we call that is a conditional probability. And we denote that with the symbol, the probability that B happens, given event A has already occurred. So if we're just talking about, drawing cards out of a deck, and I want you to tell me the probability of drawing a 4, given that I've picked out already the ace of spades. 4 out of 51. Yeah, 4 out of 51, because there's still 4 4s left. We haven't taken any of those, but we have removed one of the 52 cards, so now it's only out of 51. Is everybody okay with that idea? Okay. Or if we went back to that gummy bears example, if we're doing it without replacement, the probability of drawing a green gummy bear, given that we've already taken a green gummy bear out, was 4 out of 8. Okay. So, one way we can calculate a conditional probability is with this formula, which is the probability of A and B divided by the probability of B. Now, in most practice, you don't need to use the formula unless you're given, like, something that doesn't have, like in my cards example, we don't need this formula to do that, right? It was fairly straightforward. But if you're given like a story problem where you're just given like a couple of things happening, where it's like, the probability of me getting to work on time, is this, and the probability of my alarm going off is that, and I want to know the probability that my alarm doesn't go off that I can get to work on, something like that, is where this kind of a formula would come in. And I wrote it both ways, so whether which event is happening first. So if B happens first, you divide by B. If A happens first, you divide by A. But note that the numerator of this fraction, P of A intersect B and probability of B intersect A, still the same number, right? Because the intersection is commutative. So the only thing that's changing is the denominator, and that's fixed with which event has happened first. All right, so here's an example where we need to use the formula. So we've got a two-way table here where E is the grade from your engineering and physical science course, and L is the grade lower than a B. So if I want the probability of L, so we add up this column, right? And then divide by the total number of students. Is everybody okay with that? So here's me adding up the columns. So 3656 out of 10,000. All right, the probability of choosing or having an EPS course, given that the grade is lower than B. So we'll use our formula, right? The probability of lower than B and EPS course is 800. Well, there's 800 in there. And then divided by the probability of lower than a B, which was this guy. Notice both of these would have been out of 10,000. That's why I can just like use them as a count rather than a probability. So it's probably worth stating that this could just be N of A intersect B over N of B, right? The number of things instead of the probability. All right, the probability of L given E. So the probability that we are lower than a B and EPS, that's still 800. But here we're dividing by the EPS courses, so 1,600. Is everybody okay with the calculation here? So again, this is the probability of choosing an EPS course given that the grade is lower than a B. And this is the probability of choosing a grade lower than a B given that you're choosing an EPS course. Okay. So if our events are dependent, our multiplication rule changes. If I have the probability of A and B, it's going to now become the probability of A times the probability of B, given that A has already occurred. We want to observe that this is the same formula as our conditional probability formula. We just multiplied P of A by both sides. And get me this. You guys see that? All right. So one way that is often quite helpful in dealing with conditional probabilities is drawing a tree diagram. Remember, we did tree diagrams earlier. This is a case where it really is quite helpful. So we want to consider the situation of flipping a coin twice and calculating the probability of getting two heads. Oops. So I toss a coin. I have one choice here. That's my first flip. They could come out heads or tails. There's a probability of 1/2 for each of them. If I got heads, I'd flip the coin a second time. Again, my two outcomes, heads or tails, the probability of each is 1/2. And if I'd gotten tails, again, I'd flip my coin again. Two outcomes, heads and tails, each with probability of 1/2. So the branch that I'd be looking at for my conditional probability is this branch here, the HH. So it'd be 1/2 times 1/2, which is 1/4. Ms. Gulick, but flipping a coin is a independent event. Why the heck do I need to do this? It's just a simple example. All right, let's do another one. The Pew Internet and American Life Project finds that 93% of teenagers use the internet and 55% of online teens have posted a profile to a social networking site. What percent of teens are online and have posted a profile? So if I draw a tree diagram, online 93% and 7%, posted a profile 55 and 45, and if you're not online, you can't post a profile, right? So it's just 0 for yes and 1 for no. So we're looking for this branch here, 0.93 times 0.55. Everybody's okay with that? What's a more interesting question would have been, what percent of teens have not posted a profile? So there's 2 not posted a profile possibilities, right? So you could be online and not post a profile, or not online and not post a profile. So it'd be 0.93 times 0.45 plus 0.07 times 1. All right. In an experiment, a researcher has placed 6 green toys, 4 red toys in a container. A child is asked to select 2 toys at random. What is the probability that the child chooses 2 red toys? Okay, first choice, red or green. The probability of choosing a red toy is 4 out of 10. Okay, never mind. We're going to do this first. And the second choice, again, red or green. For my first choice, the probability, okay, so that's what we're looking for. First choice is 4 out of 10 for red and 6 out of 10 for green. Now for my second choice, I've removed 1 red toy and 1 toy, so it should be 3 out of 9. Now we still have all 6 green toys remaining, but there's still only 9 toys total because we pulled a toy here. So that probability should be 6 out of 9. Similarly, down here, There's still all 4 red toys remaining because we pulled a green, but there's only 9 toys, so this should be 4 out of 9. This one would be 5 out of 9. So if we want that red outcome, it should be 4 out of 10 times 3 out of 9. Everybody's okay? And again, I want to point out that like any of these answers are correct, whether you give it as a fraction, a reduced fraction, a decimal, or as a percentage. Any of those are fine. If you're writing a percentage, though, you got to have that percentage symbol on it, because we know probabilities can't be greater than 1. Another example, a survey of 1,000 people is performed regarding their gender and whether they were colorblind. The results are below. What is the probability that a person chosen at random is colorblind given that the person is female? So if I say C is colorblind and M is male, I would say then my other symbol would be not colorblind is C complement and female is M complement. Everybody's okay here? Okay. So the probability I'm looking for is the probability of C given not M. So that's going to be this probability formula. So I go to my chart here. So I'm colorblind and not male is 2 divided by the probability of male, 510. Oh, I'm sorry, not male, 490. Woo! So I'd have 2 out of 490 or any of these answers over here. Everybody's okay? Notice that this time I wrote it as probabilities just to illustrate to you that whether you take a count or a probability, you end up with the same result, right? Okay. What is the probability that a person chosen at random is a colorblind female? So again, this is colorblind and not male. So again, probability of colorblind not male times the probability of not male. So 2 out of 490, and then 490 out of 1,000, or just 2 out of 1,000, which would have been naively what we would have said, right? What is the probability that a person chosen at random is a colorblind individual? Yeah? So just like also showing you symbolically of kind of what you're doing using conditional probabilities here also, right? Is that okay? But it's really not that bad. All right. The probability that a regularly scheduled flight departs on time is 83%. The probability it arrives on time is 92%. And the probability that it arrives and departs on time is 78%. Find the probability that a flight arrives on time given that it departs on time. So this is, we're looking for the probability of A given D, right? So using our formula, probability of A and D, 0.78, divided by the probability of D, 0.83. So 94%. Everybody's okay? Departs on time given that it arrived on time. So that's the probability of D given A. Again, it's going to be the probability of DNA divided by the probability of A. So 0.78 divided by 0.92. So just under 85%. Everybody's cool? Blah, blah, blah. We talked about independence. So another way to define an independent event is if the probability that A happens given B has already happened is just the probability of A, or that the probability of B happening given that A has already happened is just the probability of B. We can call them independent. Here you see that B happening doesn't affect the probability of A, or that A happening doesn't affect the probability of B. Or similarly, if they are independent, we have the same multiplication rule that we noted earlier. So we might ask ourselves, are the events arriving on time and departing on time independent? So let's do our calculation. So what I would want to check is the probability of A given D. Is that the same as the probability of A? Nope. Or is the probability of D given A the same as the probability of D? Nope. So not independent. You could have done it the other way also. Again, not independent. Everybody's okay with that? Also, you could have checked to see if this probability that was given to us matches this probability times that probability, right? So 0.78 versus 0.76, again, not independent. Any of those three methods work. They're all perfectly fine to use. Another example. In a certain country, the police stop drivers on suspicion of drunk driving. When stopped, drivers are either given a breath test, a blood test, or both tests, or neither. Records show that 81% are given breath tests, 40 are given blood tests, 25 are given both. What is the probability that a drunk driver is given a test? Right away, can you tell that these events are not mutually exclusive? What word in here is our indicator? Both, right? They're saying that two of the things can happen at once. When I have events that are not mutually exclusive, I want to start by drawing a Venn diagram. I think that makes everything quite a bit simpler. So here is my both, my blood, my breath, and the both. If the blood tests are 40%, I know that circle is 40%. So we'll start, and the breath is 81%, so that circle is 81%. Both is 25%, so I'll place that there. That means that if this is 40%, I've already placed 25%. That means I have 15% can go there. Similarly, we can say that 56% can go here. And neither is the remaining. If I add those up and subtract from 1, that's my neither. Okay. So the probability that a driver is given a test would be the probability we get a blood test, or both, or just a blood test, both, or just a breath test. Or you could have done, since I know they're overlapping, the probability of breath plus the probability of blood minus the probability of both, which comes out to 0.96, which is the same thing you would have gotten if you added this one, and this one from the Venn diagram. Either way of doing it is fine. So far, so good. What is the probability that the driver is given exactly one test? So that mean would be just blood or just breath, right? So 71%. So far, so good. Given, what is the probability given no tests? Well, we already see that, right? Are the events breath test and blood test independent? So let's check it, right? We'll calculate the probability of breath given blood. Or I could do this one. That'll work too. So we know what this is, right? Breath and blood should be 0.25. The probability of breath is 8.81. The probability of blood is 0.4. I get that, but that's not this one. So what is that telling you? They're not independent, right? AKA dependent. All right, let's do another. So diagram shows a target for a game. The radius of the board is 40 centimeters. And it's divided into 3 regions. You score 2 points if you hit the center, 1 point for the middle white region, and 0 points for the outside region. What is the probability of scoring a 2 in one attempt? So it's going to be the area for the 2 divided by the area of the whole board, right? Assuming that every throw hits the board. Yeah. Assuming every throw hits the board, which is fine to do in this case. So pi 10 squared divided by pi 40 squared, or 100 over 1600, or 1 in 16. Everybody okay there? Was the probability of scoring a 1 in one attempt? How do we calculate the area for the white ring here? Good. So you take the white circle and subtract out the yellow circle, or that baby puke color, I don't know what you want to call that, and then divide it by the total area. So 3 out of 16 is what it reduces down to. So far, so good. Just a little light geometry for you this morning. Reese took a deep breath when I said geometry there, was not happy. It's like, oh boy. All right, new example. And the point of this is that these at least and at most situations, it's often easier to use a complement rule than otherwise. Let's look at an example. Suppose the probability of there being rain on a given day is independent, and of there being rain on the day before or after. So the probability of it raining doesn't depend on what happened the previous day or the next day. Over the next 4 days, you would determine the probability that it will rain on any one of the given days is 30%. Was the probability of it raining on day 1 and day 2? So it's independent, right? We don't care about what happens on day 3 or 4. So it's just going to be the probability of rain on day 1 times the probability of rain on day 2. Because it's independent, I can just multiply those two probabilities together. Like about 9%. The probability of it raining on day 1 or raining on day 2. So this is or, right? So the probability is going to be rain on day 1 plus the probability of rain on day 2 minus the probability of it raining on day 1 and day 2. Since these are clearly not mutually exclusive, because it could rain the entire 4-day stretch, right? So 51%. So far, so good. What's the probability of it not raining on any one day? Here is the complement rule is going to be much easier for us because I'd have to calculate it. If not, I would have to calculate the probability of raining 4 days, raining 3 of the days, 2 of the days, 1 of the day, and how many different ways could it rain on, say, 3 days? Could not rain on day 1, but rain the other 3. Not rain on day 2, but rain the other 3. Not rain on day 3, rain the other 3. Not rain on day 4, but rain the other 3. And it gets worse as they go, right? There's a lot of possibilities here. Just calculating with a complement rule is much easier. So the probability of not raining on any one day is 70%, right? If it not raining at least once, or the probability of it raining at least once, so that's going to be the probability of 1 time, or 2 times, or 3 times, or 4 times, and that's terrible. The other option is, what's the complement of at least? So it'd be a strict inequality. Okay. What? Right, that's what we're getting here. So the complement of it raining at least once would be it raining less than 1 time, strict less than, because this is greater than 1. So the complement is strict less than. But this is a discrete thing, so then less than 1 is just 0 for us, right? Because you can't have half a day of rain. Just rained on that day. It rained on, So the probability is just of never raining. So it can't rain would be not raining on day 1, not raining on day 2, not raining on day 3, not raining on day 4. So 0.7 for all of those. So the probability that rains at least once would be 1 minus it never raining, or about 76%. Everybody's cool? What's the probability of it raining at most 3 times? At most 3 times would be 3 or 2 or 1 or 0. I don't want to do that. Let's do the complement. The complement of at most 3 is exactly 4. So greater than 3, the only outcome greater than 3 is exactly 4. So it's just going to be rain 4 times, so 0.3. So that probability of raining at most 3 days, 1 minus the probability it rained every day, 99%. Woo! And we got to the end. Thank goodness, Mr. Kulik. That was a big set of PowerPoints. And now my recording window's all jacked up here. I don't even know what it's doing.